Module 6 sees us turning our hand to tools and techniques that are used when we actually try and model how asset prices behave and how returns are likely to evolve. So this reading, or this module, is called Simulation Methods. The crucial takeaways here are you need to understand what the very common assumption about log normal price behavior is. So we often assume log normal distributions when we're thinking about how prices behave. And that feeds through to some implications as to how our returns, particularly our continuously compounded returns, are likely to behave. So you need to be able to describe that. And then you need to just be aware of how methods like Monte Carlo and bootstrapping are used. So these are terms that are commonly bandied about. You need to know broadly how they're used and what they're used for. So let's jump in then. This idea of using the log normal distribution to explain how prices of assets behave over time. First thing we need to understand here is what the log normal distribution is. Now, this can be quite confusing. What I like to think when I see the word log normal is I replace it in my head with log is normal. Okay, and that really gets me out on the right side of this every time. If you say that a variable is log normally distributed, then the definition of that is that it's logarithm. So you can always take the logarithm of something just by hitting the ln key. The logarithm is a function. It gives you the power of e that gets you back to y. All right, but let's not get dragged into the weeds there from a technical perspective. Just think of the logarithm like a function, just like when you square something or when you double something. It's just a function, okay? And what we're saying is, if you are looking at a log normally distributed variable y is log normally distributed, then its logarithm, when you take logarithms, what you end up looking at is a normal distribution. Its log is normal. Don't forget ln is the abbreviation for logarithm, okay? So that's something to get in your head. If something is log normal, then its logarithm is normal. I actually think of it as the log is normal distribution. That's stuck for me. If something is log normal, so if y is log normal, then it doesn't go below 0 and it's got right hand skew. It's got right tail skew. It's not bounded above. So it is bounded below and not bounded above. And so this is why it's quite a useful distribution. I'm talking here about the definition of the log normal distribution. This is why it's quite a useful distribution when we're thinking about how prices might behave, right? It's bounded below by 0. It's not bounded above. So it's got longer right-hand tail than left-hand tail. That's positive skew. And this is why it's useful for prices, because the prices can't go below 0 and they're not bounded above. I mean, they can't go up forever, but there's no ceiling. There's no technical ceiling on them like there is a floor of 0 on prices. Okay. Now, actually, this log normal distribution is it's not just prices it's used to model. It's used to model what's called price relatives. So it's used to model where prices will be in the future at time big T versus where prices are today. All right. So it's used to model essentially the next period's price or a future price relative to where prices are today. That's what's referred to as price relatives. And if you think about it, this is quite a sensible distribution to use for this price relative, because once again, prices could go up a lot. So PT over P0 could be very big relative to where we are today, or PT could go close to 0. That would be a disaster for those holding the asset, but that would take us down here. But we can't go below 0 under the assumption that prices are bounded below by 0. Now, if we go back to the definition of the log normal distribution, in your head you think log is normal. So if we're assuming that price relatives are log normal, then the logarithm of price relatives is normal. Okay, that's a key implication of assuming log normal distributions for price relatives. And here comes something quite profound and very useful in modeling, because it turns out that we've already met the logarithm of these price relatives. Okay, if I drew in there that your price relative PT over P0 is 1 plus your actual return, because it is, isn't it? 1 plus your holding period return, because that's what it is, right? End price for a particular period divided by start price is just 1 plus the holding period return for the period you're looking at, for the time frame 0 to big T, then actually you could say this here is the logarithm of 1 plus your actual return. Now, does that ring any bells, if you excuse the pun? Does that ring any bells? The logarithm of 1 plus your actual return. We know from an earlier module that that is simply the continuously compounded return of this security that you're looking at, this thing with these prices. So this is a really crucial connection to make. If you assume price relatives are log normal, then their logarithm is normal by the definition of the log is normal distribution, right? And actually the logarithm of price relatives is the logarithm of 1 plus the actual return, which is your continuously compounded return. So we are assuming, essentially, by assuming that price relatives are log normal, we are assuming that continuously compounded returns are normal. Okay? Now, if you didn't catch that, it's okay, you'll never have to prove it, but let's approach it again from, if you like, the other direction. All right? You remember from a previous module when we looked at continuously compounded returns that we can always say that an end price that we grow into is a start price compounded forward. And how do we compound forward at a continuously compounded rate of return? Do you remember the compounding factor was e to the RCC, e to the decimalized return? That was in a previous module. Well, you can then divide both these sides by P0 and see that your price relative can be viewed as e to the RCC. And then do you remember we also said that the logarithm, the natural logarithm in particular, which means you're looking at powers of that e number, all right? The natural logarithm is the opposite function to the exponential function. So if you take logarithms of both sides here, you get the logarithm of the price relative on the left, and you'll get the logarithm of e to the RCC on the right, and the logarithms and the exponentials cancel out because they're the opposite of each other. We've said that before. So there you go. There's another way, another route in to see what we already seen, and that is the logarithm of price relatives is actually your continuously compounded returns. That's what we said here, by the way. Logarithm of price relatives is your continuously compounded returns. So 2 ways, 2 for 1 there, 2 ways of getting to the same conclusion. Key takeaway: if we assume that price relatives are log normal, then we are essentially assuming that continuously compounded returns are normal. And that's a very common assumption in lots of traditional finance models, lots of Nobel Prizes being handed out for those coming up with models and theories based on normally distributed continuously compounded returns, which are essentially the same thing as saying price relatives are following a log normal distribution. I'm just going to echo here something we said in an earlier module, and that is the question, why do the analysts like using continuously compounded returns? And the answer to that, do you remember, is that continuously compounded returns, they scale up nice and easily over time because they just add together. You know, if you've got a continuously compounded return in period 1 and a continuously compounded return in period 2, you can just add them together to get the total continuously compounded return in 2 periods. You can add them together, divide by 2 to get the average continuously compounded return on a periodic basis. So that's nice and easy, but it's also very useful from a statistical perspective because we find that normality is propagated by addition, all right, for normally distributed variables, which we're assuming continuously compounded returns are. It's not necessarily propagated, it's not necessarily sustained, if you like, by multiplication, which is what we do for actual returns. We multiply through by 1 plus r, don't we, to move over multiple periods. All right, so we've spoken there about how easy it is to scale up continuously compounded returns. What about volatility? How do we scale up volatility? If we start off with daily volatility, how do we scale up to, say, weekly volatility that's got 5 days, 5 working days, or annual volatility that tends to have 250 working or trading days? Well, under a simplifying assumption, and that is that our periods are identical, we need that so that we know that volatility stays the same. And that's an assumption called, that's the periodic volatility stays the same. That's an assumption called homoscedasticity. All right. The homoscedasticity, the implication is, of course, that if your volatility changes periodically, then you've got heteroskedasticity, which is actually often a problem, as we'll see later on when we talk about regression. So if we assume homoskedasticity, if we assume that returns are independent, in other words, the correlation of any return at any time versus a return at another time, say the day before, is 0, okay? And so they're identical, independently distributed returns. Then really what you're saying is, say you wanted to scale from 1 day to 2 days. You know in any individual day you'll get a volatility of sigma d. And then on the next day, you'll get a volatility of sigma d. The question is, what is the volatility over 2 days? That's the question, right? Your homoskedasticity assumption means that these daily volatilities don't change, right? Each one of these is a day, essentially. But what is the volatility going to be over 2 days? Well, as you know from a previous module, we don't combine standard deviations. We combine variances and then take square roots, right? So really, in order for me to work out volatility over 2 days, I should be thinking about the variance over 2 days, okay? And combining the variance that I get on each individual day. And if I do that, then I can say my variance over 2 days, just like the 2 asset portfolio we saw earlier, there's going to be a squared term and 100% exposure to day 1, and a squared term and 100% exposure to day 2, and then there's going to be 2 lots of my 100% exposures, and then sigma d, so volatility in each day, multiplied by the correlation. There's going to be a correlation term in here of the 2 days, right? Now that correlation term is 0. We've already said that, right? Correlation over 2 days is 0. So actually what we're saying is, under these assumptions, that 2-day variance is just the sum of individual day variances. In other words, 2-day variance is 2 lots of the 1-day variance. Now if I solve now for what 2-day volatility must be, I take square root of each side and I notice a root 2 popping up over here. And that is the nub of this issue here. When you scale up volatility over time, you don't scale up by time, you scale up by the square root of time. That's the key takeaway. You scale up volatility under these assumptions, by the way. Scale up volatility by multiplying through by the square root of time. So if you're going from a small time period, little t, to a longer time period, big T, you scale up by the square root of big T over little t, not by t over little t. You can use big T over little t for variance, all right, but not standard deviation. You need to take square roots. So if you're told the daily volatility of the FTSE 100 is 0.86, so that's sigma d, it's always good to label things, right? Calculate the annualized estimated volatility of FTSE 100 returns, assuming 250 days in the year. So annualized means yearly. Assuming 250 days in the year, what we're going to do is we're going to say sigma 250 is going to be sigma 1 scaled up by the square root of 250 over 1. You could just put 250 in there. It's the relative size of the big period versus the small period, isn't it? So the root of 250, not too hard to get it on the calculator. That's one of those kind of reverse buttons where you have to do it after the number. I'd actually go 250 root, deal with that first, 250 root, and then multiply by 0.86 in whole percent terms, and you're done, right? Very straightforward idea. Okay, now moving on to the centerpiece really of this module, and that is Monte Carlo simulation. So Monte Carlo is a very practical approach to simulating paths that an asset could move down, and then thinking about, you know, what these values are likely to be that we could end up at, and therefore what maybe a payoff of a derivative would be, and therefore take an average and we can think about what that's worth to us today. That's what Monte Carlo simulation is. It's really coming up with recipes to model assets and think about the paths they could go down to give a range of values that we could see in the future. So rather than describing Monte Carlo simulation, let's just jump in and do a very simple one, such that the idea comes across. Let's say we've got a stock trading at 50. We're just going to make a very simple assumption that quarterly the stock either goes up by 6 or goes down by 5 with equal likelihood. So if you think about it, we've got a year in front of us, which is our time frame that we're interested in, that we find out here. And you could go up 6, you could go up another 6, right? Each of those got a probability of a half, go up another 6, and then up another 6. That's not very likely, but that's the best outcome if you're holding this security. Actually, you know, this is a pretty good outcome. Don't forget you go down by 5. Right, so a pretty good outcome if you go 3 ups and 1 down. You'll go up to 68, then fall by 5. So you'll end up at 63. There's more than one way of ending up at 63, isn't there? There's that route where you go up, up, down, up. You know, you get the idea. All right, so there's actually more than one route to all these destinations here. I'm not going to draw this all in. You know, there's another destination here where we have 2 ups and 2 downs. All right, so that would be up to 62, then down 10. So we only end up at 52. So this is the kind of the binomial lattice that we're generating here. I'm not going to draw it all in. We're being asked, what's the value of the right to buy the stock? Now that's a call option. We haven't done derivatives yet, so don't panic. But if you've got the right to buy something at a fixed level, what's called the strike or exercise price, then you've got a call option. I'm just going to draw the strike in on this grid so we get a picture of what's happening here. The strike would sit at 55. Don't let it move. It would sit there. And what we're doing really is standing at this time and saying, well, would I? Let's let this security randomly move into the future and then think about how many times I get 74 and I exercise my right to buy at 55. You know, how many times do I get 63? What would I do then? How many times do I get 52? What would I do then? You know, that sort of thing. Okay. So using the Monte Carlo approach, first thing you need to do really is not necessarily specify how the asset's going to behave, but specify what the goal, the objective of the modelling is. So we're going to try and model the option's value. The option is the right to buy at 55, an asset price. And really what we're trying to assess is the, really we'd go for the present value, that would be the current value of the option, of the payoff that we get at expiry. Now the payoff is what the share price turns out to be, all right? Relative to the strike. Okay. Now it wouldn't be negative though, would it? Because you know, x. So x is a word, is a letter used for strike. It comes from the fact that you can use you can call it the exercise price. So right, so that's where the x comes from. Okay. Now look, the payoff would be this value if it's positive, but it would be 0 if this value were negative, because no one's going to pay 55 for something that's worth less than 55. Okay. Variables that we need to model are what the asset price is likely to be, which we've already spoken about, and the risk-free rate if we're going to do discounting back to today. Okay. All right. Now construct a time grid. We know that we're going to go over 4 quarters. I've kind of already done that. And then specify the random nature of your process, all right? Because that's what Monte Carlo really is. It's specifying sort of distributions and sampling from them. So we're going to say, look, to formalize this idea that the stock can go up by 6 or can fall by 5 with equal likelihood, equal probability, we're going to have a variable b, which is a binary variable. It can take 2 values, 1 and 0, with equal chance. And if b takes a value of 1, then the stock will go up by 6. If b takes a value of 0, the stock will go down by 5. You know, there's lots of, you know, a spreadsheet would do this for you very easily. Lots of very basic coding stuff would simulate this random variable, giving you +6, -5 with equal likelihood. And then what you do is you start drawing from your random process that you've defined. Now, this won't happen every time, of course, but let's say, for example, our first draw is B takes a value of 0, 1, 0, 1. Now that means we're looking at a stock path that goes down, up, right? And it will go up in the end by 2. What we've actually specified is one of these paths that end up here. There's lots of paths that end up here, right? We've specified one that went down, up, right? That one that I just drew in, okay? So that's what we see. And what you need to do, that's the random process in action. What you need to do is now translate that into what the effect would be on the asset price. So given that we got a 0, which meant we went down by 5, we know we're going to go 50 down to 45. Then we got a 1. This is me just interpreting this output. All right, 0, 1, 0, 1. What we're going to say is our stock price goes down by 5 in the first period, up by 6 in the second period, down by 5 in the third period, and up by 6 in the fourth period. To get that 52 where you've got +2 gain. You then can interpret what you do with the derivative. So remember, the call option is the right to buy and the strike is 55. So would you pay 55 for something that's worth 52? The answer is no. Right? You wouldn't pay 55 for something that's only worth 52. So you throw the option away. It's worthless. It wouldn't be exercised. No one would pay 55 for something that's worth 52. All right. Take that 0, discount it back to today. All right, and you are done. Okay. Repeat the simulation trials over multiple paths. Okay, to carry out your simulation. Okay. The average option value that you get through all of your paths is the Monte Carlo estimate of the value of the option. Okay, that's the general idea. There is a little bit more. This is a very simple example, and we might need to do a little bit more. For those of you looking at this that know a bit about modelling and risk-free discounting and things like that, we're just not talking about that here. We're trying to demonstrate what Monte Carlo simulation is. So the extra step of qualifying to use the risk-free rate as a discount rate. We're not going to cover that here. We're making a simplifying assumption that we can discount. We have the rate that we can discount back by. Okay. Now, the Monte Carlo, that was one iteration. You're going to do this many, many times. Right? You got 0 in that iteration, but you know from this grid that I've drawn, sometimes you might go up, 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 right? Up 4 times. It's not very likely, is it? It's only got a likelihood of a half times a quarter times, half times a half, which is a quarter, times a half, which is an eighth, times a half, which is 1 in 16 times, but it will still happen. We won't do the maths, but there's a little bit more chance that you end up at 63. You might notice that if we end up anywhere else, we throw the option in the bin because we don't pay 55 for something that's worth less than 55. Okay, so if I do 100 simulations, what I find is most of the time, if you like, this is the number of paths that I see that I generate going into the future. They add up to 100. Most of the time, I have a path for the underlying asset that doesn't get above that 55. 20 times my option value was 8. Now, why would that be? Well, that must be when I got here, 63, as a final destination. Because when you pay 55 for something that's worth 63, you get a net profit of 8. Well, you get a payoff of 8, right? So these represent where the underlying iterated. There was 3 ups and 1 down. All right. Less likely is your 4 ups. This must be your 4 ups where you get a huge option payoff. 19 implies if you're paying 55 for something and you're making a profit of 19, it implies the thing that you're buying is actually worth 55 plus 19, which of course is that 74 that we first thought of here. All right. So that's where you get a payoff of 19 versus the strike. All right. But that doesn't happen very often. That only happens 10% of the time in this particular batch. Okay. That only happens 10% of the time. So by carrying out these samples, we can get an idea of what our options value is going to be. All right, and then we can really just wait, take an average. We can say, look, 70% of the time we got a value of 0, so that's trivial. All right, 20% of the time we got a value of 8, and 10% of the time we got a value of 19. If you add that up, you get to a value of 350 undiscounted. So we're not going to go through the process of discounting because we'd have to create a risk-free portfolio with the option if we're going to use the risk-free rate. We're not going to do that here. We're just demonstrating that you can actually calculate an average option value at expiry using this Monte Carlo approach. So the crucial takeaway is really the idea. You know, we specify a random recipe, that a path, you know, that defines lots of different paths that an asset price could move down. That was this number 3 here. We know what we're going to do. We know about our time horizon and our time grid. And then we specify how the asset price is going to behave. And then we model lots of paths and take an average. That's the essence of Monte Carlo simulation. Now notice how Monte Carlo simulation gives you a range of values. Not just one value, but there's a range. Could be 0, could be 8, could be 19. All right, for our option. So this is useful to think about maximum losses, maximum gains, you know, how likely it is that we lose money. There's 70% chance here we lose all of our money. Okay, so it's useful for both return and risk, thinking about chance of losing a certain amount or our portfolio falling below a certain value. And it's very useful for complex securities where there's no neat formula, like a neat little closed formula like the Black-Scholes formula. It's a neat little formula we can use to value something. This is what's called a numerical method, where we, by brute force, we just specify what we think a process is, and then we just run it, not just 100 times, but thousands of times to think about what comes out. So it's very, very robust and very flexible. You can also think about changing assumptions, change strike prices, change that volatility of going up, 6 down 5, and think about what happens if your assumptions are wrong. Really, that's what you're doing if you're tweaking assumptions and seeing the impact. You're thinking about what would happen if your assumptions are slightly out, if you've got estimation error. So Monte Carlo simulation, you can view it that we're dipping into an assumed process and sampling from it again and again and again, right? Of course, you've got to get your assumed process right, otherwise your model's no good. A bit more of a pragmatic approach to continuous sampling from a source is to not use a model that we've imagined, which is what Monte Carlo does, but to use a lot of historical data. Now that's what bootstrapping is. Bootstrapping is where we take a very large sample of historical data and we treat it like a population. So we might take the last 60 years of stock market prices in the States. Maybe we've got daily returns. That's a lot of data, and we can draw samples from it. We also replace items that we pick out. So if you pick out a certain day, you put it back so you could pick it again. It's what's referred to as sampling with replacement. So a large sample is treated like the population, and you draw a smaller sample from it, all right, with replacement. What you can do, draw one sample and get a sample mean X bar 1. What you can do is do another sample, right? This is bootstrapping. Do another sample, strip out another sample. It will be slightly different, and you'll get another sample mean X bar 2. Now, what you're really interrogating here is you're looking at how the sample statistics that you get from your population might change. So once you do this a lot, you're looking at lots of different X bars. All right. Remember, X bar is a sample mean, and you can now, through a very brute force method, you can now understand how your observed sample means and even your observed sample variances and skewness and kurtosis are likely to behave as estimators for true population parameters. This is quite profound, and we're going to really, it's quite important, this idea that we're using sample statistics to estimate what population parameters are. We're going to really deep dive on that when we get into statistical inference, and we're going to use it in hypothesis testing. But it's enough to say for now that you've got to be really careful when you're doing stats to understand the difference between a sample statistic, like a sample mean, that's just an average from a mean, and the true population parameter. So the true population parameter would be mu when it comes to means, right? This red X bar, which is random actually, and depends on the sample, because it changes per sample. This red X bar, we often use it as an estimator for the true population mean. We can get a hand on how good an estimator it is as it bounces around by resampling from a big sample, which we assume is the population. That's what bootstrapping is. All right, we're directly observing how X bar changes as we take different samples. Okay. For now, I'm just going to leave that there. We're going to come back to bootstrapping actually in a later module, so I'm going to leave that there. That can be used in valuation as well. So when you're using this bootstrapping in valuation, what you're really doing is drawing potential paths from historical data. Instead of drawing your paths from a hypothesized model, like we did with Monte Carlo here. All right, there's your hypothesized model, and your paths were driven by the model. What we're doing with bootstrapping from historical data when we're carrying out valuation is we're just sampling and resampling again and again from historical data. All right, and you're saying, well, that's a path we could go down. Here's another path. Take a sample of 100 days. That's another path we could go down over the next 100 days. Okay. So very similar to the process we just looked at. Same number of steps. It's just steps 3 and 4. We get our paths from a sample of out of historical data. All right, rather than generating it from a model, simulating it from a model. All right. Well, that completes this relatively brief module. Try and take away the key ideas there. I don't think there's going to be a lot of calculations there, but take away the key ideas. Make sure you know about log normal prices, price relatives implies normal continuously compounded returns, and make sure you know the basics of Monte Carlo simulation from a model and bootstrapping historical data out of a large historical sample.